Okay, we're going to be talking about calculating the change in entropy. In Chem 1A, we learned about standard enthalpy change for a reaction, delta H with a little degree sign here, and that was the change in the enthalpy for a process in which all the reactants and all the products were in their standard states, right? That doesn't happen very often, but it's kind of like a benchmark value. So we need to remind ourselves, what does a standard state mean? If it's a gas, it means the pure gas at exactly 1 atmosphere. So do we encounter gases in their standard states very often? No. Nitrogen is probably the closest, but even it's not 1 atmosphere. If it's a liquid or a solid, we're talking about the pure substance in the most stable form at a pressure of 1 atmosphere and temperature of interest, which is usually 25 Celsius. And if it's a substance in solution, it has a concentration of 1 mole per liter. Now, many substances that are soluble in a solvent are not that soluble, and so you couldn't even make a 1 mole per liter. But this is the reference point, okay? So that was 0 for enthalpy. So the standard entropy change for a reaction, delta S with a degree symbol, is the entropy change for a process where all the reactants and all the products are in their standard states, okay? Just like enthalpy, entropy is a state function, meaning it doesn't matter how you got there, it's just where did you start and where did you end up. So in 1A, the analogy is a change in elevation. You're at the bottom of a mountain, and you're going up to the top, and it doesn't matter if you went straight up or took the really long, windy route, or my favorite, which isn't in the book, is get a helicopter to take you up there, right? The change in elevation is the same, doesn't matter how you got there. So the delta S then is the entropy of products minus the entropy of the reactants, the final thing minus the initial thing. So now we need to define what is standard molar entropy. For enthalpy, we had to pick something to be 0, just like with elevation. We chose sea level because it's convenient, right? So for enthalpy, we chose elements in their standard states as having 0 enthalpy. But in entropy, there actually is a real 0. And that would be when you have a perfect crystal, no defects in it, no contaminations, at 0 degrees Kelvin. So at 0 Kelvin, at absolute 0, the motion of the molecules stops, right? So that's the third law of thermodynamics. The entropy of a perfect crystal at absolute 0 is 0. This is because there's only one way to arrange the components of that that will have the same energy. Just it's perfect crystal. It's just that's it. There's only one way. And Boltzmann's definition of entropy was that entropy is a constant times the natural log of W, being possible ways to arrange. Well, if W is a 1, then log of 1 is 0, and entropy is 0. Okay? Any questions about 0? Entropy is also an extensive property, meaning it depends on how much stuff there is. So enthalpy is also extensive. So if you burn a teaspoon of gasoline, you get a little bit of heat out, right? If you burn a gallon of gasoline, you're going to get much more heat, right? More stuff, more energy. The same is true for entropy. If you have more of it, you're going to have more entropy. So these are molar entropies. So this is the entropy per mole. So for 1 mole of H2 gas at 298 K, this is the standard entropy for that. Okay? So these are all listed in a table. And there's a table in the appendix of your book that lists a lot more. So if you can't find it here, you can look in the back. So At 25 Celsius, the standard entropy is the energy dispersed into 1 mole of the substance, and it's going to depend on how many places there are to put the energy. How many ways can we arrange the particles where they will have the same energy? So this is going to be affected by the state, solid, liquid, etc., molar mass, which allotrope it is, molecular complexity, and extent of dissolution. We're going to talk about each of those. So gases, liquids, and solids. We learned earlier that the entropy of a gas is larger than that of a liquid. Makes sense. Liquid, the particles are all close together. They're limited in the volume. And in a gas, they're spread out all over the place. They could take up all kinds of different volumes. Entropy of a solid is less than that of a liquid. The particles are fixed in place. They can vibrate and stuff, but they're not moving around. So gases have more energetically equivalent ways to arrange their components. So here, looking at water in the liquid state, water in the gas state, the entropy is higher if it's in the gas state. Molar mass affects this as well. Here we're looking at the noble gases, and this is the same order they are in the periodic table. Their molar mass is increasing as we go down, and we see that their standard molar entropy is also decreasing. The molar mass is increasing, and the standard molar entropy is increasing. So larger molar mass, higher entropy. Why, if you care? The energy states associated with the motion of heavy atoms are more closely spaced than those of lighter atoms, and so you have more possible ways for the energy to be dispersed. That's all we'll say about that. The trend only holds if the substances are in the same state. These are all gases. If some of them were liquids, molar mass would not help us at all. Allotropes. Allotropes are different forms of the same element. So here are 2 allotropes of carbon, diamond and graphite. Both of them are just carbon atoms. It's an element, carbon. But what's different is how the atoms are arranged, how they're bonded to each other. In a diamond, we have covalent bonds between the carbon atoms, and it goes in 3 dimensions. In graphite, we have layers. Here's one layer, another layer, another layer. Within the layer, the carbon atoms are covalently bonded to each other. But the individual layers are held together only by intermolecular forces, like induced dipole forces or London forces, which are very weak. And that's why graphite is slippery, right? Because the layers slide very easily. So the graphite is less constrained, and so it has greater entropy. Here, these carbon atoms are more tightly fixed in place, and so that has lower entropy. And then molar complexity. Entropy will increase with increasing molar complexity, again, because there's more places to put the energy. So if we compare argon and, argon is an atom, right? So an atom can do translational motion in the gas state. It can just, move through space. It can do rotational motion. It can spin on itself. It cannot do this vibrational motion. This is where we have a covalent bond, and the bond is stretching and contracting like a rubber band. And, you're like, oh, don't keep doing that. It's going to break. Well, no, it isn't, but you can imagine, right? So nitrogen monoxide has a higher entropy, even though it has almost the same molar mass, and they are both gases. And it's because this is more complex. It has one bond in it that can vibrate. Okay? Any questions? If we look at carbon monoxide and ethene, C2H4, nearly the same molar mass, I mean, like it's surprisingly similar, 28.01, 28.05. C2H4 has a higher entropy because it's more complicated, right? So let's just sketch Lewis structures really quick here. Carbon monoxide, C2H4. Carbon monoxide has one bond that could vibrate. Here, we've got 5 different bonds that could vibrate. And they could be vibrating at different rates, and so there's all kinds of more things that could be happening. So more complicated, right? Comparing these guys, NO, NO2, and N2O, the molar mass is increasing as we go. We're adding an extra oxygen. Sorry, that's N2O4. And so the molar entropy is increasing, but we also have the complexity increasing. And so the molar entropy will also increase. So what do you need to know out of all of that? Well, you should be able to, given a very limited choice, be able to predict which thing has higher entropy than another. Okay. Dissolutions, I forgot this one. You take a crystalline solid and you dissolve it in water. What happens? The ions that were all lined up in a nice little crystal, now they separate and they move around in the water. And so they take their energy with them and they're spread into a larger volume. Energy has spread. You can also say there's more energetically equivalent places, ways to arrange things. The energy was concentrated in the crystal, now it's dispersed through the solution. So if we take a solid ionic compound and dissolve it in water, the entropy is significantly higher. Okay, so calculating standard entropy change for a reaction. This is calculated the same way that we calculated delta H. We're going to add up the entropies of all the products, and we're going to subtract the entropies of the reactants. So the N here is the coefficient in front of whatever substance that is. You multiply the coefficient by the standard molar entropy because it's joules per mole Kelvin. And so if you have 2 moles, you're going to have twice as much, and then the moles cancel out. You add them all together. You do that for the reactants, you subtract them. Okay? Standard enthalpies of elements are 0 in their standard states. Standard entropies, this is not confusing at all. Standard entropies are always non-zero at room temperature. The only time they can be 0 is at absolute 0. Okay, so calculate delta S for this reaction. So delta S, delta is final minus initial. We're looking at the entropy of the final thing and subtract the entropy of the initial thing. So this represents the total entropy of the products minus the total entropy of the reactants. So we have 2 moles of water, and we're going to multiply that by the entropy, the molar entropy, 188.8, and that's joules per mole Kelvin. When we multiply those, the moles cancel out, and we've got joules per Kelvin, the unit of entropy. We also have in there 2 moles of SO2, so we look up its entropy, 248.2. and those moles are going to cancel out. That's the products. This doesn't fit well on a slide. And then from that, we're going to subtract the reactants. So there's 2 moles of H2S. You don't need to write that. H2S is 205.8 joules per mole Kelvin. And 3 moles of oxygen times the entropy of oxygen per mole. 205.2 joules per mole Kelvin. Any questions? So then, you get out your calculator and you do math, which some people love and some people hate, and that's okay. And I'm getting minus 493. Did you put parentheses around this?
The book says 153.2.
Oh, does it? Oh, I see what I did wrong. I was testing you.
Thank you.
You passed. Okay, I'm just going to start over because I don't know what I was doing.
I don't know.
2 times 188.8 plus 2 times 248.2 minus the quantity 2 times 205.8 . Okay. There we go. So, any questions?